Welcome to the Aquascope 3 training CD, and thank you for purchasing a Gutermann leak detector. In this CD we'll provide you with all the information required to set up the Aquascope 3 and become a good leak detection operator. The theory of leak detection. The main objective in leak detection is to hear the sound of the leak, with the use of powerful acoustic microphones designed to find water leaks. The position that generates the highest leak noise is closest to the leak. Electronic listening sticks are used to sound on valves, hydrants and water meters to localize the leak position. The tripod microphone or ground microphone are moved along the path of the pipe above ground to pinpoint the position of the leak. Leak noises. To be a good leakage operator, we need to recognize all the different types of noises in the pipes so we can take the appropriate action. The typical sounds are leakage, which is usually a high-frequency whistling sound, flow, a low-frequency droning sound, obstructions and insertion probes, usually a more intense flow sound, consumption through a water meter, a mid-frequency running water sound, not too different from a leak, but with a ticking sound as the wheel of the meter rotates. Pressure-reducing valves make a strong whistling or roaring sound that can be heard for over a kilometer at times of peak flow. Partially closed valves will sound very similar to a leak when there is a reasonable reduction of pressure across the valve. Water traveling through a sewer pipe that crosses over almost touching a water pipe can induce noise onto the water pipe. Changes in the diameter of the pipe affect the sound. As water travels through a reducer, noise is generated. Big reductions and high flow create more noise. The same effect is often found on S-bends. Low-frequency mechanical noises generated by pump stations, swimming pool pumps, and air conditioning can be heard. If the pipe is lined, this will usually dampen the sound of a leak, and the sound generated may be louder at the point the water escapes from the lining than the position where the water is actually leaking from the pipe. When power transformers and high voltage lines are close to a pipeline, a low-frequency humming sound can be heard on the pipe. The ability to recognize these sounds enable a good operator to understand the readings generated by the Aquascope and develop strategies to overcome problems like using filters, closing valves, or returning during low flow periods. Leak noise. The effect of different pipe materials. Leak noise travels through the pipe wall as a mechanical vibration. The speed and distance this noise travels depends on the density of the pipe material. Soft pipe materials like poly, PVC and HDPE have poor noise propagation. Sound doesn't travel very far, often a maximum of 20 to 40 meters. However, on copper, iron and steel pipes, there is good noise propagation, and the sound travels quite long distances, typically up to 100 meters. Leak noise. The frequency of the leak. The pipe material is usually the main factor in determining the frequency of the leak noise. Each leak sounds different, but usually falls within the ranges in this table. Low-frequency leak noise is generated by pipes with poor noise propagation, and high-frequency leak noise is generated by pipes with good noise propagation. Typically in PVC pipes, the leak noise is between 300 and 400 Hz. In AC pipes, the leak noise is typically around 500 Hz. In copper pipes, the frequency of the leak noise is often as high as 1800 Hz. And in steel pipes, the frequency is typically between 600 and 900 Hz. Leak noise. Factors affecting leak noise. Hard pipe materials like steel and copper will provide a good sound, and soft pipes like polyethylene provide a poor sound. The frequency of the leak noise is high in copper, mid-range in steel, and low frequency in PVC. In small diameter pipe, below 80 millimeters, the leak noise is usually louder and a higher frequency than it is in larger diameters. In pipes above 600 mil, the leak noise can become very quiet, low frequency, and difficult to detect. Pressure influences the frequency of the leak noise, with high pressure generating a high frequency noise and low pressure generating a low frequency noise. Background noises like pressure reducing valves, throttled valves, air conditioning and consumption can drown out the sound of the leak, making it very difficult for the average leakage operator to find leaks. If the background noises cannot be filtered out effectively, the best course of action is to return when pressure is highest and flow is lowest. This is usually the early hours of the morning. Leak noise. Quality of sound. If there is a clear and loud leak noise, location of the leak should be straightforward. If the leak noise is dull or muffled, you will need to use the filters to tune into the sound of the leak. If you are unsuccessful during the day, you should return at night when pressure is higher, the leak noise is louder, and background noise is reduced. How leak noise is generated. Water escapes through a hole at high speed when there is a big pressure differential between the inside and outside of the pipe. As this water jets past the pipe wall, it creates a mechanical vibration which travels along the pipe wall. A larger pressure differential creates a louder noise at a higher frequency. The effects of different soil types. There is a large differential in pressure between the inside and outside of the pipe when the backfill allows the water to escape rapidly. So this leak noise will be loud, clear, and high frequency. In clay soils, water escapes from the pipe at a much slower rate, as there is usually a water cavity immediately outside the leak, with a clay wall only allowing the water to seep through it. In this instance, there is a much smaller pressure differential between the inside and outside of the pipe, generating a quiet, low frequency, and muffled leak noise. Ruptured leaks. When you've got a complete rupture, there is little noise, as there is a complete loss in pressure with no resistance to the water escaping. Trying to find these leaks with acoustic equipment is very difficult. However, they're quite visible, often jetting up into the sky. Small pipe ruptures. In a small pipe rupture, the water is jetting out of the hole at high speed. So these leaks are very loud, with the leak noise being strong and clear because the water is escaping very quickly with little resistance. The factors affecting the properties of leak noise are: high pressure makes a louder sound at a higher frequency than low pressure. Hard and sandy backfill create a louder sound at a higher frequency than clay backfill. Small pinhole leaks make a louder sound at a higher frequency noise than a pipe with a broken back, whilst longitudinal splits create very quiet leak noise at low frequency. Clean pipes create a louder leak noise than encrusted pipes. Metallic pipes create a louder leak noise at a higher frequency than soft or lined pipes. Small diameter pipes make a louder leak noise at a higher frequency than larger diameter pipes. Errors in the field. There are a few things to watch out for when you're pinpointing a leak with an electronic sounder. T's, changes of depths, reducers, S-bends, obstructions in the pipe, and throttle valves can all cause you to mark the leak in the wrong place. When you mark the leak position on a T, the leak noise could actually be traveling down the branch line. You should perform a sound check in all directions before marking the spot to avoid this mistake. Reducers, partially closed valves, obstructions in pipes, and S-bends often sound like a leak, so it helps to know the system you're working on to avoid these mistakes. When the pipe depth changes or the concrete slab level changes, it is very easy to think you've found the leak because there is a big change in noise level. This is a difficult situation you may not be aware of unless you've used a locator to plot the pipe positions and the depths. You may need to drill test holes or push a mighty probe onto the pipe, making direct contact between the pipe and listening stick to accurately pinpoint the leak. Now that we've provided you with an understanding of the theory of leak detection, it's time to explain how to set up your Aquascope 3 and use it to find leaks. Aquascope 3 Setup. Connect the headphones to the socket on the control unit located to the right of the display. Assemble the listening stick. Screw 2 probe bars onto the microphone with the pointed section at the end. Typically, you'll only use 1 or 2 bars unless you are sounding in a deep chamber and all bars are required. The additional bars can induce more background noise. It's a good idea to insulate your probe bars with heat shrink to reduce the wind noise. Take the cable out of the case. This cable is extremely sensitive. Do not coil it or twist it. Always gently roll the cable around the ground microphone when putting it away. The 4-way connector attaches to either of the microphones. The groove on the connector must match the groove in the socket. Push them together and screw the connector on tightly. Connect the handle of the ground microphone to the base plate, turning clockwise all of the way. When connecting the ground microphone, use the same cable, aligning the groove and screwing it in tightly. Connect the small connector on the other end of the cable to the Aquascope 3 control unit. Make sure the red dot on the cable lines up with the red dot on the control unit. This cable also acts as the on-off switch. Leave the headphone cable bound up, as it is a little bit long and can get in the way. If it taps against the microphone cable, this creates background noise. Attach the Aquascope 3 control unit around your waist. Put the headphones on, making sure the cables are not crossed. You're almost ready to use the equipment. Using the volume plus and minus buttons on the front of the control unit, set the volume level at about 70%. The level is shown on the display. Adjust the volume setting on the headphones to about 50%. Push the end of the listening stick against the water pipe in your house or office. Hold yourself and the microphone still. Press and hold the silver button next to the display on the Aquascope 3 to hear the sound. When you release this button, the sound is muted. The slightest movement of the stick will be heard as a scratching sound through the headphones. Ideally, you should stand with the stick in an upright position to reduce movement. The screen shows the volume level, signal, filter status, and battery status. When a reading has been taken, it also displays a 2-digit number. This is the noise level from the current or last reading. The signal is a real-time display of current noise level. To display a historical list of previous noise levels, press and hold the M button on the front panel. This will display the last 8 readings from right to left. Filters are used to tune into the sound of the leak and eliminate background noises. To turn the filters on, press the green plus and minus buttons on the front panel simultaneously. Change the filters by scrolling up with the plus or down with the minus. The range is between 200 to 5000 Hz, and the bandwidth is plus and minus 100 Hz from the value displayed. For example, if it's tuned to 600 Hz, you're listening to noise between the bandwidth of 500 Hz and 700 Hz. Minimum noise profiling. The numeric value displayed on the front panel of the Aquascope 3 is a noise level, based on minimum noise profiling. That means the number latches to the quietest sound heard. It does this because a leak is a constant sound that never goes away. Other noises often come and go, drowning out the sound of a leak for a short while, but the leak noise is in the background and is always there. So when we're looking for a leak, we're looking for the loudest, quietest noise. The minimum noise profiling on the Aquascope 3 latches to the quietest noise to enable the operator to quickly reference the quietest noises. In order for these quietest noises to be accurately referenced, each reading should be for a minimum duration of 20 seconds or sufficiently long enough for passing noises to pass. Aquascope 3 Application. Methods of sounding. There are a number of different ways of using the listening stick to localize and pinpoint leaks. If there are no underground services in the area, a mighty probe can be pushed into the ground onto the pipe to provide sounding points on the pipe to pinpoint the leak. Most mighty probes are insulated now and are poor leak noise conductors, so they cannot be used as sounding points. Instead, you remove the mighty probe after making the hole and insert the electronic listening stick in the hole created to contact the pipe. The leak position is localized by sounding directly onto valves, pipes, taps, and hydrants. The leak position can be pinpointed using the tripod foot when the leak position is a wall, under concrete slab, or when it's buried in pipe underground at a depth of 500 millimeters or less. The tripod foot is the best way of finding leaks under a concrete slab because the ground microphone is often too powerful. The ground microphone is used to pinpoint leaks under roads and when the pipe is buried underground at depths greater than 500 millimeters. When using the ground microphone on grass, a piece of plywood should be inserted between the ground and the ground microphone. Recognizing leak noise. To assist you recognize the sound of leaks, we have a few examples to play for you. The first track is an example of normal flow in a steel pipe. There is no leak here. The next track is the sound of a meter ticking on a copper service line. This track contains an example of a leak in a cast iron water main. This track contains an example of a leak on a PVC pipe. This track contains an example of a leak on a copper service. This track contains an example of a leak noise taken from a stop valve on a cast iron pipe when the leak is about 8 meters away on a copper service. Good use of filters is essential in finding quiet leak noise that is muffled with background noise. To prepare your skills for using filters, it's advisable that you familiarize yourself with tuning into the sound of a leak at every opportunity you have. In this track, you hear the same leak as in the previous track. However, the sound was recorded from a ball hydrant. You can hear there is a big increase in the amount of low-frequency background noise. In the next track, we're still listening to the same leaking copper service, but this example is from the meter and about 15 meters away from the leak. The next track is at exactly the same location, but the consumer is using water and the meter is turning. Now in this track we're using the ground microphone and have it placed on the road, above the same leak as in the previous examples. The pipe is about 900 millimeters deep, the filters are off, we hear the birds in the background, the leak for a few seconds, and then the sound of a plane passing. By activating the filters and tuning into the sound of the leak, this background noise is almost eliminated. This is demonstrated in the next track taken from the same location, with the filters turned on after about 20 seconds of the recording. This soundtrack provides an example of the process of tuning in the leak noise with the filters. After 10 seconds the filter is turned on. Then the plus button is pressed, going up the frequency scale. Once the top of the scale is reached, the minus button is pressed until the bottom of the scale is reached. And then the plus button is pressed to tune into the sound of the leak. In the field, localize the leak position by listening on all water meters, valves and hydrants in the area to identify the locations with the highest leak noise levels. Each reading should be taken for at least 20 seconds. You may want to record your readings on a plan and mark your area of interest. Locate the pipe between the two loudest points using a pipe locator. Pinpoint the leak position by following the path of the pipe you've located with the ground microphone. Take a reading every 700 millimeters for a minimum of 30 seconds at each point. You may need to use filters for quiet leaks or busy areas. Once you believe you've pinpointed the location with the loudest sound, confirm this position by moving the microphone back and forth to confirm no other spot in the immediate area gives you a sound equal to or more than the position that you believe the leak to be at. Leaks in clay can often be displayed as twin peaks. It isn't two leaks, and the leak isn't at the loudest point. The ground is saturated at the leak position and a poor conductor of leak noise. The leak is often halfway between the two loudest points. In the building, check the meter to confirm there is a leak and estimate the size. Draw a sketch of the building, record your results and determine your area of interest. Check the leak source is not a faulty tap or leaking toilet. Localize the leak position by taking readings for 20 seconds or more with the electronic listening stick at taps, garden taps, showers, hot water boilers, water meters, fire hydrants, and any other places the pipes are accessible. Locate the pipes between the 2 points with the loudest noise. Follow the path of the pipe you've located with the tripod foot, taking readings for about 20 seconds every 500 millimeters to pinpoint the position with the loudest leak noise. Perform a circular check to confirm the leak position by taking additional readings around your leak position to confirm they are all quieter than your leak reading. Please contact your local Gutermann office or distributor with any further questions. You now have all the knowledge to become a good leak hunter. Watching this presentation several times in the first few months and plenty of field practice will increase your learning curve.